and the sodium atom. These two atoms in the atomic level, they have a higher energy, and in the molecular level, when they are combined, when they are combined, they have less energy. How the energy is less, what happens to the energy, that is what we are going to discuss today. Say for example, the first statement, cesium in gaseous state, that is an atom separated or isolated. Cesium in the gaseous state, when it loses one electron, when the one electron is removed from the cesium, and the cesium plus gaseous ion is formed, and the ionization energy corresponding to this loss of electron is plus 374.05 kilojoule per mole. Actually, these are all calculated per mole. And when you are taking a chlorine gas, an atomic gas, one atom of chlorine is taken, and when an electron is added, you are getting Cl minus gas, where the electron affinity, actually the chlorine is showing a positive electron affinity, but in the energy scale, we are getting negative. Negative means the energy is coming out. In the case of ionization potential, we are supplying energy for the removal of the electron. In the case of electron affinity, the system gives out energy. This is exoenergic process, whereas this is endoenergic process. So the sign is minus here and the sign is a plus here. But actually, when we discussed electron affinity, we might have said this is plus. That is electron affinity tendency. The tendency is a positive. So the chlorine has a positive tendency for getting an electron. But electron affinity in energy point of view, it is minus 361.92 kilojoule. So when you are adding a cesium plus ion and a Cl minus ion, actually the enthalpy change accompanying this process is plus 12.13 kilojoule. So the formation of cesium plus and Cl minus from cesium gas and chlorine gas, it is not feasible energetically, because practically it is not possible to separate one cesium atom or one chlorine atom, and also energetically it is not at all possible to make ions individually. See, the chemical system will not simply obey whatever we tell them. These systems will go on their own processes. See, the potential energy between the ions is minus Q1 Q2 by R, where Q1 is the charge of one atom and Q2 is the charge of another ion, divided by R, where R is the distance of a separation. Suppose if you measure the ionic radius of cesium and ionic radius of chlorine, you can see the distance between these two ions will be 114.7 angstrom unit. But in crystal, it is found to be 2.36 angstrom unit. They are much closer. So far less energy in crystal than the cesium and the chlorine. In the crystal structure, the energy is much less. But cesium plus and Cl minus ions present at their respective positions in the crystal lattice are distinctly more stable than the free cesium atom and Cl atom. So this is what is the understanding we have. When the cesium plus ion and Cl minus ion are present in their respective positions in the crystal lattice, the potential energy possessed by these ions are much less than the potential energy that would be present if a cesium gaseous atom and the chlorine gaseous atom are put together. So the atom's potential energy and the ion's potential energy, if you compare these two potential energies, the potential energy of the ions in the crystal lattice is much less comparing the potential energy of atoms. Actually, what is happening is, when you are bringing two atoms together, the two atoms are far away from each other. Actually, as long as they are far away, there exists an attractive force. This attractive force is because of the nucleus of one atom attracting the electronic cloud of the other atom, and the nucleus of the other atom attracting the electronic cloud of this particular atom. And because of that, an attraction predominates when the atoms are separated at a far distance. But when the atoms are brought closer, when they come closer and closer, there comes the repulsion due to the repulsive force between electronic clouds and the repulsive force between the nuclei. So when they are critically closer, repulsion predominates. When they are far away, far separated, attraction predominates. So there is a particular position where the repulsion and attraction, they balance each other, and that balanced position is the place where the potential energy is minimum. So potential energy is found to be minimum at that particular distance where the repulsion and the attraction balance each other. Suppose if you take cesium, atomic cesium and atomic chlorine in gaseous state, and when they are brought closer, see, this is the internuclear distance and this is the potential energy. When the internuclear distance is far away, then energy is less. When they are brought closer and closer and closer, see, here the internuclear distance is less, here the internuclear distance is more. The atoms are far away here, potential energy is less. But when they are brought closer and closer and closer, the potential energy goes on decreasing and reaches a minimum, and then further enforcement to make the atoms come closer will increase the energy rapidly. There is a sharp increase in the energy when the atoms are brought much closer. So there exists a point. If you go beyond this, energy increases. If you go beyond this, energy increases. So there is a critical distance. So this is the distance at which the repulsion and the attraction balance each other and the energy is found to be less. But this is the case in the case of atomic cesium and atomic chlorine. But if you take a cesium plus ion and a Cl minus ion, the trend is the same, but the potential energy becomes the least. That is, the potential energy of the ionic system, potential energy of the atomic system, they are vast difference. So when the ions are brought closer, potential energy goes on decreasing, but at a faster rate, and reaches the minimum. That minimum potential energy is much less than the minimum potential energy that was observed for atomic cesium and atomic chlorine. So this is what happening when the ions are brought closer. And then if you further compel the ions to be closer, then the potential energy increases rapidly. But in the case of crystals, what happens if a cesium ion or chlorine ion is taken as the central ion, then it will be surrounded by not one single chlorine ion, it will be surrounded by 6 or 8 other anions. This is called the coordination of ions in a crystal structure. Similarly, each chlorine ion will be surrounded by either 6 or 8 cesium ions. So depending upon this environment, if you consider the environment in the crystal, still further minimization of potential energy is observed. So this is what is we are understanding. So any cation in a crystal structure is surrounded by more number of anions, and any anion in the crystal structure will be surrounded by more number of cations. Actually, this is called coordination number in crystals. Actually, if you cancel out the coordination numbers, and finally you will get 1:1 for cesium chloride. One cesium ion will be connected to one chloride ion. Suppose if coordination number is 8, one cesium ion will be surrounded by 8 chloride ions, and one chloride ion will be surrounded by 8 cesium ions. So 8:8, you will be getting 1:1. The molecular formula will be satisfied. So this is how the ions are present in the solid state in the crystalline structure. So what we ultimately understand by this discussion is potential energy minimization is observed when the bond is formed. So during the bond formation, there is minimization of a potential energy. So when the atoms or ions are separated for a long distance, the potential energy is high. It is not that much high, but it is high comparatively. When these ions or atoms are brought closer, there is a minimization of energy observed, and at a critical distance the energy is much less. It goes to the least level, and further enforcement to make the atoms or ions go much closer will increase the potential energy, and the potential energy goes on increasing. So there exists a critical distance which is called the R0. The R0 is the critical distance at which the potential energy of the atoms or the potential energy of the ions are minimum. But when you compare the potential energy of the atoms or ions at the same distance, the minimization in the case of ions is much more when compared to the minimization observed for the atoms. Now look, the factors influencing ionic bond. What are all the factors that influence ionic bond formation? The first factor, ionization energy. Ionization energy is the minimum energy required to remove one electron from the outermost orbit of an isolated atom in its ground state electronic configuration. If ionization energy is found to be very less, then greater is the tendency for the formation of a cation. See, the alkali metals and alkaline earth metals, they are found to have less ionization energy. So they have the greater greater tendency for the formation of a cation. And the second factor that influences ionic bond formation is that electron affinity. If the electron affinity is very high, greater is the tendency for the formation of anion. So the less ionization energy makes the elements more metallic. High electron affinity makes the elements more non-metallic. So metallic character itself is to lose electron, and the non-metallic character itself is to gain electron. See, one species should be in a position to donate the electron freely, and the other species should be in a position to get the electron at the expenditure of energy. It has to spend energy. So it is ready to lose energy to gain the electron. So this is what is observed. When the ionization energy of the metallic atom is less and the electron affinity of the non-metallic atom is high, then what happens? It will be very easy for the formation of an ionic compound. So low ionization energy and a high electron affinity facilitates formation of ionic bond. And apart from this, there is another factor which influences the ionic bond formation is lattice energy. What is lattice energy? This particular point you should understand. See, whatever we are discussing now, you should remember always. So the things what you might have studied in the school days might have been an installment studying and an installment forgetting. Actually, whatever you have studied right from your LKG until now, you should have in your mind. See, this same lattice energy what we are discussing today, we will be discussing the same point in a different level, in a different concept in the third year BSc chemistry. And the same thing will be discussed in a much greater manner in the MSc chemistry. So if you forget all the things what we discuss now, it will be very difficult for you to follow in future. So I want to wait to you 1 minute. So this lattice energy, it is the amount of energy released when cations and anions are brought from infinity to their respective equilibrium sites in the crystal lattice to form 1 mole of the ionic compound. So I'm going to form 1 mole of the ionic compound. So I'm bringing the ions from the farther distance and I want to bring them to the equilibrium sites, that is their respective positions in the crystal lattice. What is the amount of energy released? See, for example, even you might have seen the crystallization of sodium chloride. If you go to the area of Thuthukudi, you can see where the salt is made. Actually, what they are doing is they take the water containing large amount of sodium chloride, which is called the super saturated water, and the water is evaporated and the crystal sodium chloride is formed. Actually, sodium chloride is a cubical crystal. The simple cubical crystal is sodium chloride. Actually, the sodium ion which is present in solution at a farther distance, the chloride ion which is present in solution at a farther distance, they are all brought to the cubical positions. And what is the energy released during the formation of 1 mole of the crystal? That energy is called a lattice energy. See, if the lattice energy is very high amount of energy is released. What does it mean? It means that the tendency for the formation of for the crystal is very high, which means that the force of electrostatic attraction between the constituent ions is very high. Actually, this attractive force, this is a force. This attractive force, F is equal to minus Q1, Q2 by R square. So you should understand, if it is force, it is divided by square of the distance. If it is potential energy, it is divided by simply the distance. So the force is equal to minus Q1, Q2 by R square. So these are all the three factors affecting or influencing the formation of ionic bond. One is ionization energy, and the second one is electron affinity, and the third one is lattice energy. Now, smaller the distance between ions, greater the force of attraction. Hence, anion and the cation should be small in size and should have high electric charge. That will result in the high electrostatic attraction. Now look here, this particular point you should understand. The size and the charge. Put together, it is called charge density. Charge density is the charge divided by size. Say for example, sodium plus ion is having +1 charge. Cesium plus ion is also having +1 charge. But sodium ion is smaller, cesium ion is bigger. So if you measure the charge density, what is the density of the charge in sodium plus ion and the density of the charge in cesium plus ion? Charge density in sodium plus is high, but charge density in cesium plus is less, because the size is sodium plus ion is of a smaller size and the cesium plus ion is of bigger size. So what happens when charge density is high, then the force of attraction will be high. The electrostatic attraction will be high. So smaller the distance between the ions, greater will be the force of attraction. And we have already told you that even if you compress the ions to be closer than this smaller distance, then repulsion will be resulted. Bringing the ions still closer will result in repulsion. But this smaller distance, we are speaking about the equilibrium distance. So what happens? Sodium plus ion, chloride ion. Cesium plus ion, chloride ion. I'm keeping the chloride common. I am changing the cation only. So what happens? The less in energy, that is ionic attraction or electrostatic attraction is found more in sodium chloride and less in cesium chloride because of the size. So for a given anion, if a cation is small, the attraction is high. For a given cation, if the anion is small, the attraction is high, which means that the lattice energy will be high. So look here, this is a tabular column to express the idea of the influence of the size of the ion in the formation of ionic compound. Look here, actually the values given in the table are expressed in kilojoule per mole. I am taking fluoride ion only and I am varying the size of the cations. So lithium, sodium, potassium, rubidium, cesium. So lithium is the smallest, cesium is the biggest, but I keep the size of the anion constant. So what happens? For lithium, the lattice energy is minus 994.5. When the size slightly increases, lattice energy decreases. When the size further increases, lattice energy further decreases. When rubidium, still low. For cesium, the least. Now I keep the lithium cation the same and I change the anion. So fluorine, chlorine, bromine, iodine. Iodine is the biggest, fluorine is the smallest. Look here, it is minus 994.5. When you come down, it is minus 802.6. It is minus 760.8 and minus 710.6. So the energy decreases. So for a particular cation, when anion size is increasing, lattice energy is decreasing. For a particular anion, when the cation size is increasing, the lattice energy is decreasing. So the lattice energy will be the highest for small cation with a small anion. And the lattice energy will be the least for big cation and the big anion. See, for lithium fluoride, it is minus 994.5 kilojoule per mole. For cesium iodide, it is just 564.3 kilojoule per mole. So when the ions are smaller, then the electrostatic attraction is higher. When the ions are bigger, the electrostatic attraction is smaller. So it is because of the distance between the ions. So the electrostatic attraction between the ions, it is actually manifesting in the form of lattice energy. So lattice energy will be high for smaller ions and the lattice energy will be less for bigger ions.